This lecture is about Thevenin equivalent circuits. We are going to use two methods to solve the circuit to find the Thevenin equivalent voltage and Thevenin equivalent resistance. The first method is the simplest method that can be used on the circuits that have only independent sources, independent current and voltage sources, and no dependent sources should be there. In addition to that, it should have resistance, inductance, and capacitance if you're solving an AC circuit. But if you're solving a DC circuit, then it should have resistance and only independent sources. And this method actually you have learned in DC and AC class. So let's start with this method, which is method number 1. And this is employed when circuit has only independent sources, whether it's current source or voltage source or a combination of both. The method is pretty straightforward. Let's choose a circuit. Let's say this is your circuit. And let's assume that you have a load resistance connected between nodes A and B. Assume node B is grounded. Let's say this is 45 ohms. This is 0.7 volt, 122 ohms, 75 ohms. This is a current source, 0.3 ampere, and 220 ohms. And let's say this resistor is load resistor RL. To solve this circuit using Thevenin equivalent, what we need to do is, the first thing that we do is to remove the load resistor wherever it is connected. Remove the load resistors and leave the terminals where the load resistor is connected to be opened. The first thing is to remove the load resistor. Then you have to find the Thevenin equivalent resistance for the circuit when you look into the terminals where the load resistor was connected. So into this terminal from right to left over here. And to find the Thevenin equivalent resistance, what you have to do is to remove the voltage sources and the current sources from the circuit. Wherever you have voltage source, short circuit that source. Wherever you have current source, open those terminals. And the resultant circuit, for the resultant circuit, you have to find the equivalent resistance looking into the terminals where the load was connected. So let's do that. So to find Thevenin equivalent resistance, I'm going to redraw the circuit. I'm short circuiting the 0.7 volt source, and I'm going to open circuit where 0.3 ampere current source is connected, and I'm also going to remove my RL between terminals A and B. what we are left with is 45 ohm, 122 ohm, 75 ohm, and 220 ohm resistor, and we are going to find the equivalent resistance between terminals A and B, looking inside the terminals from right to left, and that will give us the Thevenin equivalent resistance. Alright, so let's do this. Oops. Now, to solve for the Thevenin equivalent resistance, of course, between terminals A and B, you can see that 45 ohm resistance and 122 ohm resistor are in parallel, and then the resultant will be in series with 75 ohm resistor and 220 ohm resistor. Make sure you always have to start combining the resistor from the opposite end where you are finding the resistance. So if you are finding the resistance on the right hand side, you have to start combining the resistor from the left hand side. So our Thevenin in this case will be 45 ohms in parallel to 122 ohm, that will be in series with 75 ohm and 220 ohm. Let's solve this real quick. Let me just use MATLAB. Write down the number 45 parallel to 122 plus 75 plus 220. So RD will be equal to parallel combination of 45 and 122 plus 75 plus 220. This is over here, this is nothing but 1 over 45 plus 1 over 22 and inverse of the whole thing. That will give you the parallel combination of 45 and 122 plus 75 and 220 in series. So my equivalent resistance will be 327.87. Go back here. 327.87 ohms. That is going to be my Thevenin equivalent resistance. Now to find the Thevenin equivalent voltage, we have to go ahead and put the sources back in the circuit, still leaving the RL out of the circuit, but we do have to go and put the sources back in the circuit. So this is for Thevenin equivalent voltage. We go ahead and redraw the circuit. 0.7, 45, actually I have it here, so 45, 0.7, 122, 75 ohm, 0.3, 220, and I'm gonna leave RL terminals open. 220 ohm, 0.3 ampere, 75 ohm, 122 ohm, 45 ohm, and 0.7 volt, and these are my terminals A and B. What we are trying to do here is we are trying to find the voltage between the terminal VA and B, that is the open circuit voltage between A and B, and that will be our Thevenin equivalent voltage. So everything is the same. One thing that you should realize here, that since there is no resistor connected between A and B, hence there will be no current flowing through this 220 ohm resistor. That means there won't be any voltage drop here. Hence the voltage A and B, VAB, will be the same as the voltage across this 0.3 ampere source. So I can move my port A right over here, and I can find the node voltage A, since B is grounded, so the node voltage A minus node voltage B will be the same as node voltage A. Now if B wouldn't be grounded, if the load resistor is connected somewhere where both the terminals, if one of the terminals is not grounded, then you do have to find the voltage, the node voltages for both the terminals, or the terminal voltages, and then you have to subtract to find VAB or V open circuit. You have to subtract the terminal B voltage from terminal A. Here, since B is grounded, if you subtract it, it is going to be the same as VA, because ground is 0. So let's see which method we can use to find the open circuit voltage, which will be the best method to be used to find the open circuit voltage. We can either use nodal analysis, or we can use mesh analysis. If we use mesh analysis, then we already know the current in this mesh is 0.3 ampere, as this current source is in the exterior branch of the source of the loop. So we will have only one loop. If we go for nodal analysis, then we have this node and then we have this node, so you will have to write two equations. So I think it will be better if we just go with mesh analysis. So let's say this is our mesh current in this, which is 0.3 ampere, and let's assume that our mesh current here is I1. Let's write down the equation. Mesh 1, well, there's only one mesh that we do not know the current for, so we're just going to write down the equation for this mesh, which will be 0.7 is equal to 45 plus 122 times I1, and since both the currents are going in the same direction, so plus 122 0.3. So I1 is going to be 0.7 minus 122 times 0.3 divided by 2 plus 5 is 7, 2 plus 4 is 6, 167, and that is going to be, let's see, I'm just write down I1 is equal to 0.7 minus 122 times 0.3 divided by 167, so negative 0.2150 ampere. Go ahead, negative 0.2150 ampere. Okay, all right, so let's see what will be the node voltage A. There can be different ways we can find the node voltage A. The node voltage any node voltage can be found by starting from ground, or a node that you know the voltage of. Let's assume ground. Of course we know the voltage of the ground, so let's start from the ground and take any of the path that leads towards node A, and let's add or subtract the voltages along the path. So let's assume, let's take this path and go towards node A. So that will be, since when we cross 0.7 volt we will gain 0.7 over here, so let's say VA will be equal to 0.7 when we cross this 45 ohm resistance. Since current I1 and the direction in which we are going is the same direction, hence when we will cross 45 ohm resistor, some voltage would have dropped across I1, so when we get to this point we have less voltage, so minus 45 I1. And then when we move through 75 ohm resistance, since 0.3 ampere current is in the direction opposite of the direction in which we are going, that means this point has more potential and this point has less potential. So when we cross 75 ohm resistor and get to this point, we would have gained some voltage. So 75 0.3, that will be our VA, which is V open circuit. Now once again, this is one of the method that you can use. You can use any other method to find open circuit voltage. You just have to find the voltage method. Which method you are using to find the voltage, that depends upon you. 45 I1, I already have the value of I1 over here, plus 75 times 0.3. Okay, so I'm not using multiplication, my bad. 32.87 32.87 volt. That is my Thevenin equivalent voltage. So when I'm drawing my Thevenin, 327.87 and 32.87 multiple. So when I'm drawing my Thevenin equivalent circuit, it will be your Thevenin equivalent voltage, your Thevenin equivalent resistor, and connected between terminals A and B. RT H VT H, 32.87 volt, 328.7 ohm, and then your load resistor is connected here. Oops, RL. And that's about it. That's the first method. So to recapture the method, the first thing you're gonna do is to remove the RL from the original circuit, open circuit all the current sources, independent current sources, short circuit all the independent voltage sources, and find the equivalent resistance looking into the load terminals. Make sure start combining the resistor from the opposite side, and then move towards the side between which you are trying to find the equivalent resistance. Once you get the equivalent resistance, then go ahead and put the sources back and find the open circuit voltage between the terminals where the load was connected. Once you find the open circuit voltage using any method, whichever method you want, that will be your Thevenin voltage, and the resistance is going to be your Thevenin equivalent resistance. Now in the real circuits, the concept of using Thevenin equivalent circuit is to find out what load value will receive the maximum power from the circuit. Since circuits are usually very large and you connect the load at the output. For example, if you're connecting your speaker system to your entertainment center, then you need to know that what input resistance of the speaker system will get the maximum power from your entertainment center. So we can find the Thevenin equivalent circuit for the entertainment center, and then we can apply the maximum power theorem. And the maximum power theorem says that the value of the load resistance should be the same as the value of the resistance that is connected in series with the voltage source. So in this case, the value of the Thevenin resistance should be the same to the value of equivalent the load resistance, in order for the load resistance to get the maximum power. So to get the maximum power, from the circuit, that is the original circuit, RL should be equal to R Thevenin. And what will be that maximum power? Power maximum will be equal to, since both of them will be equal, that means half of this voltage will be dropped here, half of this voltage will be dropped here. So we can use V Thevenin divided by 2, which is the voltage that is dropped across the resistor, square divided by RL. That will be the maximum power received by your load resistance, V square over R. So this is the first method. Let's discuss the second method, and this method is when you have dependent sources in the circuit. When you have dependent sources in the circuit, you cannot remove the independent sources, open circuit the current source and short circuit the voltage source. You cannot do that to find the equivalent resistance. You still have to find the open circuit voltage across the load terminal, like the usual way, use any method, but you have to find the equivalent voltage. But to find the resistance, we have to use another technique. So let's go ahead, let me show you a circuit. So this is a problem when you have dependent sources in the circuit. When you have dependent sources in the circuit. Alright, let's choose a problem. Let's see. Okay, let's use this problem. These problems are from your book, by the way. This is problem, which problem is this? 581. This is problem 40 from your textbook. It's a rather simple problem actually, but method will be applicable to even the complex problem as long as you have a dependent source in the circuit. Alright, this is the terminal A and B where the load will be connected. You have 1.5 kilo ohm resistor, you have 2500 ohm resistor, and you have 700 milliampere source. You have 2ix dependent voltage source, 2ix, and then you have 500 ohm resistor here with the current ix. Since 2500 ohm resistor is connected here, and we don't have a node, a common node at the bottom, That means we cannot really take a common ground and make our node be ground. Either you have to take ground over here or somewhere else. I'm just gonna go ahead and take the ground at the bottom of the current source. That means my B terminal is not grounded. Okay. So the first thing that we do when you have dependent source is to find the open circuit voltage. Open circuit voltage between nodes A and B. So we're gonna find VAB, and that will be our Thevenin voltage too. V open circuit is equal to V Thevenin. To find VAB, let's see which method we can use. Let's say we can use mesh analysis, we can use nodal analysis too. If we use nodal analysis, we have one node here and then we have one node here. You can find the value of A and B and subtract them to find the open circuit voltage. If we use mesh analysis, we have one mesh, we have two mesh, and we have to write the third thing, we have to write the equation for this. So I think I'm just gonna go ahead and use node analysis, because mesh analysis I will have 3 equations, and with node analysis I will have only 2 equations. So I'm gonna take this node and I'm gonna take this node. IX is going away from the node, 700 milliampere is going away from the node. Let's say this is I1, and let's assume this is, well, I1 will be the same, that will be going through 2500 ohm resistor, so it will be I1. That means I just have to find, if I call it I2 will still be I1. I just have to find the node voltage A, and then find the drop across 1.5 ohm resistor, that will be VAB. So at node A, I have IX plus 700 milliampere plus I1 is equal to 0. IX plus 700 milliamps plus I1 is equal to 0. Okay, so I have VA over here. What is IX? This is my voltage source. So IX is going to be a little side work let me do over here to show what IX is going to be. Since we know that okay, so write down VA starting from the ground. VA will be equal to 500 IX, and then since voltage source, when we move from here to this point, this is the negative polarity, so by the time we get there we will have this voltage drop, so negative 2IX. So VA will be equal to 500 IX, which is the voltage drop over here, negative 2IX, which is the voltage of the dependent source, so that is going to be 498 IX. So IX will be equal to VA over 498. IX will be equal to VA over 498. Alright, let's continue. So we have plus 700 milli, and our I1 is VA minus VB over 1.5K is equal to 0. Actually, we do have to analyze node B, since we have both node A and node B in the equation. Let's keep it here. So I have this Let's solve it. Let's take the inverse of that. VA over 4.98 498 inverse 0.002 498 inverse 0.0020, so that's 2 milliamp, and then 1.5 inverse is 0.667, so that's 0.667 milliamp, or milli, not milliamp, sorry. So that's 0.002 VA plus 0.7 plus 0.667. Oh, that's gonna be 0.667 milli, 1.5K milli. VA minus VB is equal to 0. So 0.002 and 0.667 milli. Let me just do this. 498 inverse plus 1.5 exponent 3 inverse. Oops. 0.00267. I didn't really make much difference. 0.00267. 0.00267 VA minus 0.00067 VB, which is 0.667 milli. Let's see, is equal to negative 0.700 milliamp. Okay, this will be our equation number 1. For equation number 2, we have nodal analysis at node B. At node B, we have I1 is equal to I2 VA minus VB over 1.5K is equal to I2 is VB over 2500, VB over 2.5K. So the second equation is going to be, let me do this real quick. Wait a minute. So when I bring VB on the other side, it's going to become negative. So I will have 1.5 exponent 3 inverse plus 2.5 exponent 3 inverse. 1.006 milli and then 0.667 milli. Oops. So I have what was that, 0.667 exponent negative 3 VA minus 1.0667 exponent negative 0.0667 exponent negative 3 VB is equal to 0. That's my second equation, and let's solve both the equations simultaneously. Let's say vector A is equal to 0.00267 negative 0.667 0.00067, and the next line is 0.667 exponent -3, -1.0667 exponent -3. That's my vector A, and then my constant is going to be -0.7 and 0, -0.7 and 0. Okay, so my voltages will be equal to A. Okay, wow, big voltages. So my voltage A is -310 and voltage B is -194. -310 310.96 volt, and VB is -194.44 volt. Should we check one more time? Okay, that means my open circuit voltage, V open circuit, which is equal to V Thevenin, which is equal to VAB, will be equal to -310.96 minus -194.44. So VAB is going to be what? Let's subtract it. V1 minus V2, -116.52, -116.52 volt. That is my Thevenin equivalent voltage between A and B. Now let's come back to how to find the Thevenin equivalent resistance. To find the Thevenin equivalent resistance, what you have to do is to short circuit the terminals where the load was connected. Short circuit these terminals and find the current that is flowing in this short circuit. So that's the first step. So we're gonna find the short circuit current. Let me redraw the circuit. So Thevenin equivalent resistance. I'm going to redraw the circuit. 500 and I'm gonna go ahead and short circuit the terminal A and B. That's 1.5K, that's 2.5K, 700 milliamp plus minus 2IX 500 ohm and IX. Okay. Now since we short circuit these terminals and 1.5 kilo ohm resistor is in parallel with that, and by the way we are trying to find out what is the short circuit current flowing from A to B. So since we short circuited the terminals, 1.5 kilo ohm resistor which is connected in parallel to the terminals will be eliminated, since no current will be flowing through this 1.5 kilo ohm resistor. Remember, current seeks the easiest route. So anytime you have a short circuit in parallel to anything, all the current flows through the short circuit. So no current will be flowing through 1.5 kilo ohm resistor. Let me just go ahead and erase that. Oops, I erased much more than that. I'll go ahead and put it back. A short circuit over here. Okay. Here you go. Alright, so now we have two loops basically. The current in this loop is the short circuit current, and we have Ix in this loop. What we can do is, let's assume ground is here. Let's say what we should do again. Current analysis can work. Let's do our mesh analysis. Again, it's going to give me 3 equations. So let's see. This 700 milliampere actually, well, it will be supplying current in both because we have 2.5 kilo ohm resistor over here. Okay. Oh, we have only one node. Let's do node analysis. Node A. At node A, we have Ix, ISC and 700 ampere all flowing away from the node. Ix plus I short circuit plus 700 milliamp is equal to 0. Ix is the same that we had in the last one, which was, let's go up, where was it? Right here. Ix is VA over 498 VA over 498. I short circuit is VA over 2.5K, VA over 2500 plus 700 milli is equal to 0. That means VA will be equal to 700 milli times, or divided by 1 over 498 plus 1 over 2500. Okay. Let's do this. That's going to be negative 700 because we're going to take 700 on the other side. That's going to be negative 700. Let's see. Negative 0.7 divided by 498 inverse plus 2500 inverse, and let's assign this to VA. Negative 0.7 divided by 498 inverse plus 2500 inverse. Okay, so I got VA to be negative 290.69, negative 290.69 volt. Hence ISC will be equal to negative 290.69 divided by 2500, which is VA divided by 2500, negative 116 milliamp, negative 116.27 milliamp, negative 116.27 milliamp. Okay. Now we have Thevenin equivalent voltage, which is the open circuit voltage between the terminals where the load is connected. We have the short circuit current between the terminals where the load is connected when we short circuit the terminals. Your resistance, Thevenin resistance, will be equal to the ratio of the open circuit voltage to the short circuit current. That's how you find the Thevenin equivalent resistance in the circuits where you have dependent sources. That's one of the methods that we usually use in our class, and let's stick with this method. So Thevenin equivalent resistance is going to be open circuit voltage, which is, let's go back up, negative 116.52, negative 116.52 volt divided by negative 116.27 milli, so approximately equal to 1 kilo ohm. I would say approximately equal to 1 kilo ohm. So that is going to be your Thevenin, your circuit, Thevenin equivalent circuit. Thevenin equivalent circuit, it is going to be A and B. R Thevenin is equal to 1K and V Thevenin equal to negative 116.52 volt. That's it. And that's how you find the Thevenin equivalent circuit of a circuit with dependent sources. Actually, the circuit that I solved, it's a pretty good circuit. It's not a straightforward circuit, so we did have to use, you know, like over here we did have to use a little bit of side thing to find out what will be the IX value in terms of the voltage. So I think it's a pretty good circuit. It gives it covers a broad range of circuits. If it's a straightforward circuit, then of course it's easier to do, but most of the time you see straightforward circuits with dependent sources, method will still be the same. All you have to do is to find out the open circuit voltage first, then short circuit the terminals and find out the short circuit current, take the ratio of both. That's going to give you our Thevenin, and the open circuit voltage of course is V Thevenin. Okay, that's about it for Thevenin equivalent circuit.